Okay, so we'll pick up here at geometric settings. We'll look at a few examples. Just a quick reminder, in a geometric setting, let's keep in mind that you still have two outcomes, success or failure. The probability of success doesn't change. We have independent observations, but then this particular time, the only difference is we go until we get success. We don't have a set number of trials anymore. So we've seen this example already. We'll take a quick look again at it though. But on this particular island of Oahu, there's a village and about 80% of those residents are of Hawaiian ancestry. So what is probably the first native Hawaiian is the third person you meet? So again, we have this setting. Number one, there's two outcomes. They're either native or not. Native, well, that's not native, or they are native. Each person is independent. And for that third condition, the probability is 0.80. And then you can see the way this question is asked, that the first person we meet is the third, right? The first native is the third person. So we're going until we get success. These are going to be a lot simpler for us than a table, simply because we can set these up. So that would be not native, not native, native. There's only one way this works. We don't have to worry about all the different scenarios. So for us, it's just a matter of plugging this in. So not native is 20%, not native is 20%, and then finally we meet the native at 80%. So there's about a 3% chance that we don't meet a native Hawaiian until the third person. All right, a little bit different look here. So this is the probability that x equals 3. Here, we're looking at the probability within 3 people, so x is less than or equal to 3. So in other words, it could be that we meet a native person right away, or not a native and then a native, or this scenario. Again, a little bit more involved here, but definitely nothing that we're going to need a table for in order to organize all of our thoughts. So we'll take a quick that would be 0.992. So very, very high likelihood that we'll meet the first native within those two people. Now, the third one down here, this part C, what is the probability you meet your first native after the second person? So after 2. Well, the problem with this is technically in a geometric setting, there is no ending. We could have met the first person right away, the second person, third person, fourth person, fifth person. We could go the entire trip without seeing a native Hawaiian. So what we're looking at here, this could be, you know, third or fourth or fifth or sixth, on and on and on. There's no ending. So this is where our complement rule is going to be really, really useful for us. Well, if we can figure out the probability that we find somebody in 2 or less, it's going to be this or not Hawaiian, then Hawaiian, which is 0.96. Well, there's a 96% chance we meet them within 2 people. So what we can do is use our complement rule, 1 minus 0.96, 0.04. So there's a 4% chance that we'll meet our first native after the second person. So whenever we see this greater than situation, we're going to have to use that complement rule. All right, one more example here. In this promotional contest, this company places winning caps in 1 of every 6 bottles. So again, right, you either win or you don't win. Each bottle independent. The probability of success, the probability that you win is 1/6. And you can see, now we look into it, is it binomial, is it geometric? Find the probability your first winning cap, right? So here we go, until success. So this is geometric. We're going until success. So for part A, the probability that we win on the fourth day. So that would be you don't win, don't win, don't win, you finally do win. So for us, that's 5/6 to the third times 1/6. So there's a 9.6% chance that that's the case. Within 4 days. So that could be, right, turning that here. So we could win on the first day, or lose and then win, or we don't have success the first 2 days, or we don't have success the first 3 days, right? Here it's 1/6 plus 5/6 times 1/6. Here we've got 2/5/6, so we'll go 5/6 squared times 1/6, and then here we got 5/6 to the third times 1/6, and at the end of the day, when we put all that together, we should get, so 0.167, 0.139, 0.116, 0.096. So there's about a 52% chance, 0.518, that we win within 4 days. Pretty good chance to win within 4 days. And then finally for part C, sometime after 3 days. So in other words, the probability that X is greater than 3. So here's that situation where we could win at 4 days, 5 days, 6 days, right? So that could be 4th day, or 5th day, or 6th day, on and on it goes. Well, we don't have access to all that information. So what we can do is, if we can figure out the probability that we win within those first 3 days, so that we win or we don't win and win. So if we can figure out those probabilities, then what we can do, right? So 1/6 plus 5/6 times 1/6 plus 5/6 squared times 1/6 is 0.422. Well, there's a 42% chance we win within 3 days. So 1 minus 0.422, right? This is within 3 days. So the opposite of that would be after 3 days. So 1 minus 0.422. So there's a 57.8% chance that we win after that third day.